9608 P32 May June 19. Question number 1. A computer stores real numbers using floating point representations. The floating point numbers have 8 bits for the mantissa, 4 bits for the exponent. The mantissa and exponent are both in 2's complement form. Calculate the denary value of the following floating point numbers. Okay. So as we can see that first 2 bits are same, it means it is not normalized. So we will have to check the next part. If it says for normalization, all right, if it is asking for normalization, so we don't have to normalize over here. If the next part is not asking for the normalization, in that case, we will have to normalize and solve. So we will just solve it without normalizing it. 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1. So this will become 0.011, 0, 1, 1, 1 into 2 to power 1 to 4, 2 to power 5. Now point travels 5 positions towards right, 1, 2, 3, 4, 5. So this will become 110.11. All right, 110.11. Okay. So this will become 1, 2, 4, and 8. 8 and 4, 12, 13.75 positive. All right. So this is 13.75 positive. This is your answer for 00, 11, 0, 111, 0, 1, 0, 1. Now, state why the floating point number in part is not normalized, because first 2 bits are the same. Achha. Give the floating point number in part A1 in normalized form. So if we normalize it, 00, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1. In this case, we will normalize it. First, we will mark first 2 different bits, and whatever the number of bits in between will be subtracted from the exponent. So 0, 1, 1, 0, 1, 1, 0 into 2 to power 5 minus 4. 5 minus 1, sorry. So this will become 0, 1, 1, 0, 1, 1 into 2 to power 4. So point will be now traveling from here to 4 points down. So this will become 110.11. So you see, they both are same. So this will be plus 13.75. Give the floating point number in part A1 in normalized 2's complement format. Okay. So this will be normalized 2's complement format would be 0, 1, 1, 0, 1, 1, 0, 4, 1, 2, 4, 8. Convert the denary number plus 11.625. 0.625 means 0.5 plus 0.125. Okay, this will be 625. All right. So now 11. 1, 2, 4, 8. This is 11. 8, 9, 10, 11. 0.5, 0.25, 1, 2, 4, 8. All right, and then 0.5, 0.25, 0.625. All right, so this will be 101. 8, 9, 10, 11. 0.5, 0.125. All right, so 0.125. 0.5, 0.25, 0.125. So this will be now, the point will move towards the left all the way. So this will become 0.1011101 into 2 to power 4. All right, 0.1011101 2 to power 4. And in floating point format, this will become 0, 1, 0, 111, 0, 1, 1, 2, 4. Okay. Now, convert the denary minus 11.625. So if it is minus, first we will solve plus 11.625. The answer will be 0, 1, 0, 111, 0, 1, 0, 1, 0, 0. To have it in the negative form, we keep the exponent same, 0, 0, 1, 0. And to the first one from the right in the mantissa, we keep it same, and then we convert all of the other bits. So this is the negative formats. Okay. So whenever we have to convert from positive to negative, or we have to show negative numbers, first we solve the positive one. Once that is solved, then we will keep exponent the same. And in the mantissa, from the right side to the first one, we will keep it same, and then inverse the rest, toggle the rest. Okay. So first one, till first one it is 1, and then 0 becomes 1, then 1 becomes 0, 1 becomes 0, 1 becomes 0, 0 becomes 1, 1 becomes 0, and 0 becomes 1. Okay, and we will keep it same. So this is negative, this is positive, and this one is negative. Part C. A student enters the following into an interrupter. Okay, output 0.2 into 0.4. The result is, the student is surprised to see that the interrupter outputs the following. This is called rounding errors. Neither 0.2 nor 0.4 can be represented exactly as they are here. So system tries to first convert 0.2 and 0.4 to its nearest form. So the number, the values which are being input, they become wrong. Okay, so first you need to write neither 0.2 nor 0.4 can be represented exactly in floating point numbers. Okay. They will be represented with the nearest number, nearest FPN possible. They will be represented with the nearest FPN possible. Okay. So input values were not the same as given. result of their addition, multiplication, can still be a not representable number. Okay, as differences are increased. What does it mean, differences? The first difference was when we were trying to represent 0.2 and 0.4 in exact FPN format, and then we multiplied it, the number that was changed just to make this operation possible was different number, and then when we multiplied, it had become more different. Okay, and the difference becomes so significant at the end difference become so significant that it appears at the end, difference becomes so significant that it appears like 1 given above. Okay, packet switching can be used to transmit data across the internet. Packet switching is not always the most appropriate method for transferring the data. Name an alternate method of transferring the data across the internet. So that is called circuit switching. Give an example of situation where the method you identified in part A is more appropriate. Give an example of situation where the method you identified in part A is more appropriate. When audio and or video communications occur. All right, when audio or video communications occur, or we can say video communication streams or whatever. Okay, justification: when using circuit switching, there is a dedicated line communication line is available. There are little or no delays. It is also called latency. Okay, so there is reduced latency. Okay, there is reduced latency. Okay, network latency, sometimes also called lag, is the term used to describe delays in communication over a network. So this is reduced latency. Next question. A Boolean algebraic expression produces the following truth table. Okay, so we have all ones here. So this is A naught, B naught, C naught, 0, 0, 0. This is 0, 0, 1, 0, 0, 1. This is 0, 1, 0, 0, 1, 0. This is 0, 1, 1. This is 1, 0, 0. This is 1, 0, 0. This is 1, 0, 1. Okay, there we go. Complete the Karnaugh map for the truth table. You can put zeros there as well, but just to keep this thing clear, we don't put zeros mostly, but you can put always. So what we can do now, the K map can be used to simplify the expression that produce the truth table in part A. Draw loops around appropriate groups of ones. So this is one group, and this is another group. So this will be group of 4 again. All right. If these ones are at the side, okay, so this might, you may call it, it is a 3D plane. So if these ones are on the side, it means that they are connected. Okay. So now write the simplified sum of products. So let's first take the red one. A is changing, B is not changing. So we put B is here, B naught. And C is changing, so we leave C. Now, blue part. A is constant, A naught. B is changing and C is changing. So this is your answer. X is equal to B naught plus A naught, or X is equal to A naught plus B naught, whatever. This is the answer. Now, part B, right? A logic circuit with 4 inputs produces the following truth table. Okay. Now, complete the K map. All right. So AB 0, 0, 0, 1, 0, 1, 3, 2, 0, 1, 3, 2. Whenever we put these numbers, we put in a way that there is always one single change among all the inputs. So 0, 0 to 0, 1, and then 0, 1 to 1, 1, and then 1, 0. Okay, that is how it works. Now, over here, 0, 0, 1, 0, 0, 0, 1, 0. Then we have 0, 0, 1, 1. So 0, 0, 1, 1. Then we have 0, 1, 0, 0. 0, 1, 0, 0. Then we are only taking those outputs where there is a 1. So 0, 1, 1, 0. 0, 1, 1, 0. 0, 1, 1, 1. 0, 1, 1, 1. Then 1, 0, 0, 0. 1, 0, 0, 0. 1, 0, 0, 1. 1, 0, 0, 1. 1, 1, 0, 0. 1, 1, 0, 0. 1, 1, 0, 1. 1, 1, 0, 1. So there it is. Draw loops. Okay, so these are 4. These are 4. One, 2, 3, 4, 5, 6, 7, 8. How many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, and 9.
Sir, we have 8 outputs, sir.
Huh?
We have 8 outputs. You have
1, 2, 3,
one
4, 5, 6, 7.
the one in the beginning. You have zero. It's a 0 output, but you have took it. 1, 1, then 0 it is. Then you actually took it in the beginning.
0100 is 1 2. Oh yes,
Yeah,
this one, this one, this one.
yes, sir.
0100. This has to be removed. 0100. Yes, I'm sorry for that. Okay, now there are just two loops. So now in first loop, this one, we have A constant, B changing, C constant, C naught, D changing. And then in second loop, red wala, A naught constant, B changing, C constant, D changing. So this is A C naught plus A naught C, or you can write it other way around, A naught C plus A C naught. They both are same. Describe the main steps in evaluation of reverse polish notation using a stack. So we run through left to right. Describe the main steps in evaluation of reverse polish notation. So if reverse polish notation is left right root, so let's say it is A B plus, so we have to run through from left to right. This is the first thing. So this A and B are operands, whereas this plus is operator. Okay, so if we run through left to right, left to right and pick one element, if element is operand, operand might be a variable or a number. Okay, then we push it to the stack. If element is operator, then we pop two stack values and perform operation. If element is operator, then we pop two stack values and perform the operation. Now you have to remember that whatever the first value that you pop will be put on the right side of the operator, and the second value will be on the left side of operator. Let's say if it is 3 and 9 and operator is plus, then 9 goes right and 3 goes left. This is what I mean over here. All right. Evaluate and push the result back onto the stack. That's it. So we run through left to right and pick one element at a time. If element is operand, either a variable or a number, then we push it. If element is operator, then we pop two stack values and perform the operation. Evaluate. Perform the operation means as in evaluate. Evaluated answer is pushed back to the stack. The infix is when the operators are in between operands. This is infix. The infix expression 8 into 5 minus 2 minus 3 over 2 into 3 converts to 852 minus. Okay, so let's take 8 first. All right, then 5, then 2, then comes minus. So minus means 2 on the right 5 on the left. So the result is pushed back. All right, then multiply. 3 on the right, 8 on the left. So this is 24. Result is 24 and pushed back. Then 30. So 24, then we have 30, then 2, then 3, then multiplication. 3 on the right, 2 on the left. So this becomes 24, 30, and 2 3s are 6. The result is pushed back. Then divide. So 6 on the right, 30 on the left. So 24 and 5. Result is 5 pushed back. Then we have minus. So minus 5 on the right, 24 on the left. 24 minus 5 is 19. Result is pushed back. So there we go. This is your result. Okay, so when we have operands, we are pushing them. As soon as we have operator, we pop first two values, put the first value on the right, the value afterwards on the left, perform the operation, evaluated answer will be pushed back, and this goes on and on and on and on until you have your answer. Okay. Sanjeet is a member of the public and he wants to send a private message to the government department. Explain how asymmetric. Asymmetric means private key and public key. ठीक हो गया? Explain how asymmetric encryption is used to ensure the message remains private. So who is sending to who? Sanjeev is a member of public and he wants to send the private message to government. So Sanjeev's computer software encrypts message using government's public key. All right. Governments do not use abbreviations as I do. Computer software will decrypt ciphered message using its private key. All right, that's it. When the government department replies to Sanjeev, it needs to send a verified message. Explain how asymmetric encryption can be used to ensure that it is a verified message. All right, so verified message means adding the digital signature to it. Okay, a verified message means digital signature added. And digital signature means the digest, encrypted digest. Using sender's private key. Okay, so this is verified message. Now, government software creates message digest government's software will add hash key and cipher message to the digest and encrypt it using government's private key. Hashing algo might also be added. Okay. Sanjeet computer will decipher the digest, recreates the hash, and compares with received hash to verify. Okay. The government's computer system are vulnerable to malware. Describe two vulnerabilities that malware can exploit in the computer system. All right. Vulnerabilities are when we actually use computer, there might be several things like we are opening an email from unknown source. We are clicking, when we open the email from unknown source and click, so phishing, farming, both might happen. And if we don't update our operating system or the software, in that case, hacking is also possible. Okay, so opening emails or messages or posts from unknown sources and clicking given links, not updating operating system software when updates are available, not updating virus definitions. Okay. Identify one method that can be used to restrict the effect of malware. Any installing any antivirus and updating it always. Installing firewall, installing and enforcing firewall. There might be other creating strong passwords or something like that. Okay, question number 6. A company sells plant watering system to automatically turn on water sprinklers when the soil becomes too dry. This is basically monitoring and control question. The plant watering system has a processor and connecting cables. Identify two other hardware devices that are required in this system. They're watering, water sprinklers, actuators, like water sprinkler, sensor, um, moisture sensor to check the water in the soil, maybe humidity sensor if air is too dry. Plant watering system that automatically is turned on when the soil becomes dry. The plant watering system has a processor and all. That's it. And ADC to convert sensor signal to digital format.